This conference will now be recorded.
All right. Thank you for coming along. My name is Dave Blodgett. If you don't know me, I'm part of the USGS Water Mission Area. I sit in a branch called the Geospatial Intelligence branch in a integrated modeling and prediction division. And I wear quite a few hats around the kind of environmental science data community, one of which is with the Open Geospatial Consortium. I'm on the OGC's architecture board, and I have been a standards working group chair for one standard so far, and I've been leading up a couple of environmental features interoperability experiments. So what I'm going to be speaking about here today is the first environmental linked features interoperability experiment. There is a second that is underway that we call SELFIE, and I'm going to give you some outcomes of the first ELFIE, and I'll allude to what we're doing in SELFIE, and it's all happening kind of out in the open on GitHub, so you're more than welcome and encouraged to come take a look at what we're up to and take part if you have the time and interest. So, okay, so ELFIE. At the very top level, the goal with ELFIE was to establish some best practices to express the linkages between and ostensibly among environmental features. And that extends into observations as well, because observations like sensors are features in and of themselves. They're places on the landscape. And they observe other features. So, you've got a sensor in a river. The sensor is the site is a feature. The river is a feature, and there's an observation relationship between the two. And there's, the river is draining a watershed. Those two are related to each other in some way. There's another river downstream of that river. And these basic relationships of environmental features in that sense, and the observations that we make of those features it's a part of our IT ecosystem that we all kind of understand, but there's not actually a lot of best practices in place to connect them together and express the relationships between them in a way that kind of modern web infrastructure can work with. So to that end, the kind of overarching technical goal of the ELFIE was to have a real kind of focused, simple approach to everything we were doing, so that it's understandable and approachable to a broad audience, technical audience, but a broad technical audience. And that means kind of focusing on modern web technologies, things where we don't have to write a lot of documentation because it's kind of the way that people work already on the web, and you can just search around for solutions. But they address the use cases that we're familiar with in kind of the environmental features and observations world. So that is summarized at a high level in some of the materials at our github.io page. So what I have up on the screen right now is, if you just Google ELFIE, you'll find this, or OGC ELFIE, something along those lines, you'll find this github.io page. And there are a number of links to materials here. The first one that I'll reference is this engineering report, which is available kind of as an HTML document on the web that's pretty nicely linked together. The engineering report format, if you're not familiar with it, essentially lays out high-level summary for those that just want kind of what's this about, what were the findings. Then we get into some specific kind of terminology, overview, objectives, we talk about the use cases we addressed. We discuss the best practices and kind of standards that were experimented with and vetted. We get into some detail about what we were really doing, and then wrap it all up with some recommendations. And there's some pretty technical material that was dropped into appendices as well, around ontologies and how to turn those into basically how to turn class models into ontologies and ostensibly into JSON-LD contexts for those that are interested at that level. This is some pretty low-level technical content. So that's the engineering report. We were flattered to hear from a few people at a recent ESIP meeting that it was one of the most useful, or one of the only useful OGC engineering reports. that people had read, which I don't totally believe, but it was good to hear. Apparently it's a fairly usable and useful document for people that are working in this space. So do have a look through that if you want more information about what I'm presenting here. So now I'm going to jump into the second link on this page. It's the summary of the ELFIE outcomes. And it's a HTML slide deck, essentially, that there's a recording of the kind of outcome presentation that we gave to the OGC technical committee that's linked here as well. And it's a recording of what you're about to hear from a few months ago. But I'll just walk through these slides briefly for everybody on this venue, and this will end up recorded and on YouTube. So I'm going to skip over this demo. The first slide has a link to a demonstration that just demonstrates how we envision this kind of content being brought forward. You can go and explore that for yourself. And the idea was that that was built using the content that we worked with in ELFIE, and this was one of the experiments. So getting into the goals kind of more specifically than I illustrated just a second ago, the kind of top level purpose here was to try to achieve interoperability with a decrease in the level of duplication and maintenance required across data systems, where one data system is the set of, say, rivers for the country, and the other data system is, say, the set of observations on those rivers. And if we can decrease the amount of duplication between those two systems to such an extent that people can really just manage their own content, but reference each other in ways that are sustainable and interoperable, we will have kind of achieved our goals. So that's at the very top level. That's kind of the promise of this linked data paradigm, is letting people reference each other without the need to duplicate content and have all that maintenance overhead. So to do that, we wanted to leverage kind of the power of web services, but bring to bear the transparency of documentation that you get with linked data. And there's this, and I'll allude to this again later, but there's this notion that we want to turn the web services inside out, and describe what the web services have in them, describe what they can do using the concepts of linked data and the kind of the mass market web linked data paradigm, a la schema.org and the kind of the web search infrastructure crawler concepts. So that was kind of a technical goal, and then, as I said earlier, the kind of use case here is we have all these features on the landscape that we need to express relationships between, and especially because in the case of, say, boreholes, where there's somebody's drilled a hole in the earth for some reason, 5 different organizations might come along and take a sample out of that borehole, and they all need to be able to reference the same borehole with different data that they collected for different reasons. And so that's one of the that's another kind of primary example of the kind of data that we're working with there, where there's a physical sample, there's 3 or 4 grab samples, there's imagery, and it's all linked to the same environmental feature. Okay, so then at a kind of application level, the desire was to really populate the Google Knowledge Graphs, for lack of a better way to put it, but this preview use case that allows a search engine to have a simple preview of an environmental feature and links to relevant information about that feature. That was kind of the core use case that we were really thinking about when we were working on the project. And then, of course, how easily adopted can we make this, right? That was an overarching kind of desire, was, can we use these super ubiquitous technologies to do all the things that I just listed off? Okay, so ELFIE was a very technical project. We attempted to focus on some particular technologies, but it was fairly technical. So I just want to kind of express some of the very specific technical hurdles that we were addressing. And this is a sentence extracted from the engineering report that I think is worth reiterating. And so, current OGC services, while flexible and capable, do not directly allow exposure of features in a RESTful way or provide traversable hypermedia describing available methods, data, or interfaces to related linked content. So this expresses some gaps in the OGC services baseline, essentially, making the point that the expectations of the web around ostensibly REST or GET with an accept header maybe, those were not, that expectation of how the web works is not necessarily the way OGC services work. They do a lot of back and forth with posting of XML and various technologies that are not super familiar to typical web developers. They don't necessarily support hypertext and hypermedia the way a REST pattern tends to, where you go to an API endpoint and you get back some JSON that tells you kind of what's available at that endpoint. The methods, data, and interfaces of the services are not described in a way that uses that kind of RESTful hypermedia, hypertext paradigm that people have come to expect of modern web APIs. And then how you establish linkages between OGC services was not entirely clear. So how to use these kind of basic linked data paradigms within the context of an OGC services stack is not a clear problem. So those are the real technical kind of pieces of the OGC services baseline that we were working on. Okay, so these next two slides are around the real kind of meat and potatoes of what ELFIE was about. And so if you can, so you've got a feature in the world. You can think of the information about that feature using a variety of views of the knowledge graph that you might construct about the feature itself and the things that are related to it. And we used this this analogy of views and came up with basically two views of the knowledge graph that were kind of use case oriented and useful for our conversations, and I think useful for kind of clarifying the content that you might publish about a feature. And the first one is this notion of a preview. So this is all the information that you might want to construct a web page or a knowledge panel when you search for something in Google. That is the preview of that feature. And what we established here was essentially the linked data predicates, the associations that you would want to include for a preview of a feature. So a name, an image, a description, things that are related to it, some geometry. The geometry is an interesting space. It's definitely an area that there's more work to be done for various reasons that I won't go into right now. But anyways, we had three options for geometry, and there's some trade-offs between those three options that are described in the engineering report. So that's the preview. This is really the core. This was kind of, if there's one thing that you do, it's a name and a description and a geometry preview and some links to related resources, right? That's kind of the meat and potatoes of doing linked data for features. Okay, so the next view of a knowledge graph, and this would be about the same feature, but kind of from a different perspective of the information you might be interested in about it, is this notion of the network of other features or other information that would be linked to the feature. So, and this is the kind of core things were geospatial topology. So is there a within or touches or intersects kind of relationship? And then temporal kind of associations. And this is especially important when we get into events like storms potentially, where you would want to actually express when things happened relative to each other. And that was an area we didn't explore a lot, but there's a lot of potential there when we're talking about kind of event-driven information systems, which tend to be the most impactful for decisions. Okay, so extending the concept of network from these, so these are all very general. These are from GeoSparkle and Owl Time, which is the kind of they're the most general temporal and spatial ontologies that you could imagine using here. We extend that notion into what we call domain data models. And so some of these are pretty general, like SOSA, so sensors and observations. but some and time series, but some get pretty specific. So we've got surface hydrology features, geoscience markup language. There was some experimental work on a data model for flooding. So those are pretty specific, but they all kind of fit in this notion of a network. It's the associated features, the associated observations. And there's definitely more work to do to figure out exactly how we end up using these things, and these all need more work to be published more broadly in the kind of linked data baseline formats that we expect. Okay, so ELFIE was almost entirely use case driven, in the sense that scoping of the project, we started with these evocative use cases, and then as we went into the project, some use cases were used in design discussions, and other use cases were actually used in experimental implementations. So these few were used in experimental implementations, but there's a whole slew of other ones that are discussed in the engineering report. So this one is just, say you had a data set, so US Geological Survey water mission area. Hi, say you had a data system with rivers and stream gauge monitoring locations and water quality. How would you mash all that up into something that was kind of coherent and linked together so that people or machine learning algorithms could traverse all that and discover what's related to what, right? That's a really core thing for us, is our kind of catalog of monitoring. So that was one of our kind of primary use cases for discussion, and we implemented this little map view. We had one that was relating water budget data, so precip, evapotranspiration, and stream flow, to where stream flow is monitored and the watersheds that contribute to those monitoring locations. So this was kind of a mashup of hydrographic data, hydrologic model data, and hydrologic observations or hydrometric observations. We had a couple of really sophisticated and great use cases that were brought to bear by our colleagues at BRGM in France, that were essentially round tripping from groundwater systems to surface water systems and back again, to look at water quality and water supply relationships in the kind of cross-domain surface water groundwater systems. They actually built a little viewer where you could put JSON-LD data content into the top, and it would render the features for you in a little interface that was both a map of the geospatial features and a graph of the associations between the features and potentially observations data. And this is work that they've continued on and will be featured in future work here. So this is just a screenshot to show that they kind of had the ability to add widgets of time series observations that are associated with the particular features. This was a really good test of the technology. And then the last one, and we didn't make quite as much progress on this because there's just a lot of work to do, and it's a pretty sophisticated set of data. But it was worth its weight in gold for design discussions. Was this idea that if you had a model that could predict flood inundation, how would you link that to, say, transportation infrastructure and critical safety infrastructure like hospitals? And what would the user perspective on that be? How do you go from kind of baseline reference data of roads and infrastructure to the model to notifications, et cetera, et cetera? So this was a really good use case, and we were lucky to have the team working on it along for the ride. So those are just a few of the use cases. There are several more, but that was a quick summary. Outcomes, we had an engineering report. There's some summary use cases available online. These are all live links if you go to these slides. The technology that we ended up kind of running with is JSON-LD, so JSON for linked data. So there was a collection of contexts, which are akin to schema, but they're really more just declarations of linked data predicates that are used in a document. They're very flexible and kind of open-ended. So we had a set of these contexts that we used in our experiments and are continuing to work on in the second ELFIE. And then there's a whole slew of JSON-LD example files that I'll show just a little bit in passing later on. So we'll come back to that a little bit. So for findings of the engineering report, At the time that these slides were written, it was still called WFS3. It's subsequently been named OGC API features. Is really exciting. If you're familiar with it, you kind of know that it's coming and it's really cool. It's been published, but the new OGC API for features and the new general kind of OGC API paradigm is really a complete shift in the architecture for OGC APIs, and there's just a tremendous amount of activity around it right now, and it's looking really good for the kind of use cases I've been talking about here, and a whole slew of other things. So that's exciting. We're continuing to work on that. I think everybody's going to see that be an emphasis in the next year, 2, 3, 4, however long the technology sticks around. So kind of on the downside is we need to make a lot of progress on some chicken and egg problems. The ontologies for a lot of these data standards that are in, say, UML and maybe in XML schema, they've not been published for use in linked data. And we're working through that list of data models and ontologies that need to be published so that we can reference them in linked data, but that's work to do. Data providers don't really, without those ontologies, without common practices for linked data, it's not entirely clear how to publish your features as identifiable, referenceable things. So there's a little bit of a chicken and egg. Data providers need to put these identifiers out there to be used, but without clear ways to use them, it's not really clear how or why that should happen. So that's a little bit of a chicken and egg problem that we need to overcome. And then future work really needs to consider, and this is actually work we're kind of taking on right now, but how to discover these linked data. What are the entry points to traverse this content? How does it exist within our existing infrastructures? That was kind of findings in future work. And the real crux of the issue is this, and I just kind of find this fascinating, but it's this issue of HTTP range 14. And so 14 is a reference to the W3C issue tracker number of an issue that was raised by Tim Berners-Lee that was basically asking, what is the range of the HTTP function? Where the domain of the function is a URI or a URL, if it's going to locate a particular resource. What's the range? What do you get out when the identifier is a real world thing and not an identifier for a digital object? So non-digital things like rivers, wells, people, houses, particular things in the world. It's nice to give them identifiers that are not just identifiers for a digital representation of the real world thing, but it's not clear what the HTTP protocol should do in that case. And so the solution to HTTP range 14 was this thing they call cool URIs. Essentially, it's not a totally one-to-one mapping, but cool URIs essentially resolves the issue of range 14. And they said use a 300 series redirect. 303C other is the one that people reference most often. So that was kind of the jumping off point for us into the second environmental linked features operability experiment. And that's in process. If you go to the ELFIE repository, the ELFIE homepage, you'll see a reference to SELFIE. You'll see references to some draft content. Not going to go into great detail about that here. It's all kind of a work in progress. It's being done out in the open, so you're welcome to come and kind of read our issue tracker and see what we're up to. But it's sufficiently in process that I don't want to go into it in any great detail right now. But the one thing that kind of has been shared at other ESIP events, and I want to just kind of describe to you for 2 minutes here, is the basic architecture that we're investigating that addresses this issue of how do we want to discover all this linked data? What's the basic network architecture that supports the ability to go from a real world feature to information about that real world feature? And so I'll pop open this diagram. And before I go into detail here, when we started on the second environmental linked features interoperability experiment, I and others really pushed back on the need to use a 300 series redirect from an identifier for a non-information resource to an identifier for a meta resource. And the reason we push back on it is that nobody's really in this domain or in this space, in the geospatial kind of features space, nobody's done it yet. And it does it requires a good amount of additional infrastructure and maintenance of identifiers and how those identifiers relate to URLs for digital objects. So we want to make sure that there's a good business case for it. And so we had some pretty lengthy debates and conversations kind of searching for what the real business case is. And I think we've identified it. And what it comes down to is, if we're going to identify, say we're going to have identifiers for GNIS IDs, the Geospatial Names Information System, those identifiers need to be bound to the logic of how you look information up. So that's to say, when I put this URL in for something in Google, this identifier token in the URL header, right, is bound to the Google system, and that allows Google's search engine to go look up this digital artifact and return it to me in my browser. And we don't necessarily want the geospatial names people to care all that much about how the server is implemented for the digital representation of a geospatial object. We want to open up the potential for evolution of the digital side of the house, if you will, and allow the people that are governing identifiers for real world features to do what they need to do and mint identifiers that are structured in a way that's compatible with the needs of identifying things in the real world. So that separation of concerns essentially between the governance of identifiers for real world features and the governance and ostensibly implementation of systems that provide information about real world features is, at the end of the day, the reason for this redirect. And the redirect can be very lightweight. We don't have to have strong governance around non-information resources. In some places we probably should and will. In other places it can be much looser. But there are still a lot of web pages out there that you go to a URL and you get redirected to another URL for implementation reasons. And that's essentially what we're saying here, is that it's a good idea to use a redirect. So we have this top tier of our resource model. And so what this diagram is of a resource model, and resource is in the context of a uniform resource identifier, uniform resource locator. And we're saying that the top tier of this resource model is really a uniform resource identifier. And the only thing you'll ever get when you go to that URI is a 300 series, probably 303 redirect to a uniform resource locator that returns what we're referring to as a meta resource. And the meta resource is it's one of the documents that we were experimenting with in ELFIE. It's a set of information about the non-information resource. And this 303 redirect kind of implies that there's some community organization that collects the information about meta resources that is where this redirect goes. And that's to be figured out for every given domain of discourse, every science domain, every government, whoever ends up owning the system for a set of non-information resources has to make some determination of who is going to be the central kind of arbiter or the catalog, the index, pick your terminology, but who's going to be the community system of record that implements the index, right? And that index is just that's the lookup table. That's the master lookup table between other systems, other domains, references to these non-information resources, and data about them. And so the third tier of this resource model is just all the data, right? So it's geospatial data, it's observational data, et cetera, et cetera. But so this is a very basic resource model, but it kind of represents the top level of organization of how we expect to organize information from real world things, the meta resources that describe what the knowledge, essentially the knowledge network that we're aware of as a community, and then all the data representations and observations about the real world that we hold. So it's fairly, I feel like it's fairly profound. It's pretty darn general, but this is essentially the network architecture and the resource model to support all the stuff that we're talking about in the overall kind of ELFIE, where you might have a preview of a real world feature, a network of a real world, the network related to a real world feature, and then an actual traversable web of data to bring that all together. So that is essentially what I wanted to cover. And I figured it would be about 35 minutes. So before I stop and take, well, so I have a couple of use cases I can walk through, but I will stop there and take questions if people want to ask questions, just start a conversation. I'm happy to take this wherever. We've got about 25 minutes before the top of the hour when everybody should get back to work. But that's enough for now. If there are no questions, I'm happy to go through a couple of the demos and the use cases and just kind of show what the ELFIE use cases were all about. So. Anything you'd like me to go back to? Usually I'd be the one asking questions of the person presenting, so I'm not going to do that with myself. All right, well, I will briefly go through the use case demonstrations that we had just for the sake of the recording, and feel free to drop off if you've gotten what you came for. But I'll show these real quickly. So probably the biggest and the one that I'm probably the most proud of for how this is really supposed to work is this visualization of water budgets for the US. And so you come in here and it starts animating it just stepping through the country. And so what we brought together here was a set of watershed data, so watershed boundaries and river flow lines. And each of these is referenced via a web service call to the data that gets you the geometry. And then the stream gauge location at the outlet of that watershed is the red dot or the black dot if it's not highlighted. And then for each of those watersheds, there's web service available, precipitation and evapotranspiration, and stream flow available at the outlet location of the watershed. So in this case, so each of these is kind of referenced in a linked data document. And if we come back, so I want to come back to the summary page for this demo. So this was just a link to the static data visualization, user story, data sets included or described. There's a little more content here. If you want to see all the data and code that was used, it's in GitHub. There are a couple of links here. The thing I really wanted to get to is this file here, I believe. Yeah. So this is one of the JSON-LD documents that was used for this demonstration. So what we're looking at is the we invented an identifier here for a 12-digit hydrologic unit code boundary. It's a catchment divide feature type, got a name and a description. So this is kind of the preview content. And then there's a collection of, so we've got a couple of geometries that represent it. So we've got the schema.org geocoordinates for a point that's just kind of an idealized point for the watershed. We've got a geoshape, which is a polygon, and a fully fledged well-known text geometry. And then there's this link to a higher level catchment that this is a realization of. So this is the catchment boundary. There are other realizations of this catchment. So if we go to this ID, this little preview allows you to traverse the linked data and go to other documents that are related to it. So we just kind of used the quote unquote network view of the knowledge graph to traverse to another feature. And so in this view, we can see two catchment realizations. One is where we just came from, is the HUC12 boundary, and another is the NHT plus flow line. So this is, the boundary is we're currently in the oh, that's funny, the Minnesota River's in the demo set, but it's actually not, it didn't make it into the viz. So we're in the Minnesota River, which should be here, but we're looking at data for a catchment, so one of these watersheds. And one of the realizations of the catchment is the boundary. The other realization of the catchment is the flow line network for it. So this is kind of the high level container. There's no geometry here. There's just, just a collection of information about a real world feature. And so we have two catchment realizations and an outflow. And the outflow is we'll go to it. The outflow has a nexus realization. So this is one of the data models we were working with. One of which is a hydrolocation and a hydrometric feature. We could go to that. It's an NWIS site, it's a National Water Information System, Minnesota River at Fort Snelling State Park. It's a hydrometric station. We can go back to the nexus. So this is a link back to that, the watershed outlet, essentially, that it is a hydrometric station associated with. You know, there's a bunch of information linking it, say, to the actual river network, and theoretically in here, yeah. So we have a link to an image. Oh, and there's no the demo fails. There's no data available for this site right now. One of the other sites would work. But essentially, so we can go, there's also a link to the site inventory page for this hydrometric network. So for demonstration purposes, this does the job. But essentially, this gets you to the data for that site. So this is just a demonstration of kind of nuts and bolts under the covers of how the linked data kind of hangs together, how we can go from these high level features and descend down into linked content that's both kind of the preview and the network of related information. And all those demo files are discoverable through this ELFIE demo files link. So each use case has a section. And if we scroll down here, so here's this US water budget. So the use case we were just looking at is this US water budget's use case files. We should be able to find, so these are just different feature types that are included. Stream flow. I guess I want to go into, yeah, so if we just go to one of these, the HUC12s, pick one at random. I'll just descend down the same thing and make sure that I can demonstrate that the NWIS thing should work. Let's try it one more time. Nexus realization, go to the NWIS site, and there's an image. Now, theoretically, we get a streamflow plot. Sweet. All right. So that's what I expected to get. So then the idea would be the Google crawler could crawl around this content, and all this content would be, embedded in the headers of web pages, but be of relevance to a search crawler. And the search crawler knows what a schema.org image is. So this image is declared over here. It's a schema image from the schema.org vocabulary. And at the end of the day, Google should be able to make the connection that this thing that is at some geospatial location on a map has a preview image that's a plot of the streamflow from that site. And if we do our jobs right going forward, Google should also be able to learn what a hydrometric station hydrologic location is and present information accordingly for that type of feature. So that's a little bit of a look behind the technology. There's much more here. I'll stop at that demonstration. This was kind of the demo content that I wanted to dig into with a little bit more detail. And I will stop there unless there are questions or things that people would like me to go into in more detail on the kind of the technical content side.
Hey, David, this is Cassandra.
Hey.
Hey, I think this is really, really cool. And I think, parts of this technology could be used in so many different ways. And particularly, I'm kind of interested in the work that you did with the schemas and how you kind of like pulled all of those together. And did you create any yourself? Did you have to go through that process yourself of creating any schemas?
So the goal with this work was to not do anything new,
That makes sense.
but to find the best available for what we were trying to do.
Okay.
But there are definitely things where we still have work to do, and so some of it is publishing existing data models as JSON-LD contexts and ontologies. And so that's some of the very recent work that's going on in the second environmental linked features interoperability experiment is to move out on publishing more domain ontologies and then get those domain ontologies published as JSON-LD contexts. So we have more keys to reference. And I didn't go into much detail about that, but essentially this demo is resolving the context for us in a kind of traversable linked data world. So what I mean by that is this name is linked to the schema.org name declaration, but in the raw JSON, it's just name. And the context up here, I believe it's the ELF. So let's go to the elf.jsonld. It maps the name JSON key onto schema : name, and schema is mapped onto http://schema.org. And so the way JSON-LD works, the context maps the JSON keys onto specific linked data URLs. And this demo actually materializes that. So I went into that detail to say that, some of this stuff is formalized. So is feature of interest of might get us to something meaningful? Hey, it does. Right, so that's cool. So for sensors and observations, we have a baseline to build on, but it looks different from schema.org. And I guarantee if you asked for JSON from this, you would get something different than if you asked for it from schema.org. And if we go to GeoSparkle has geometry, yeah, we get a 404. And we don't have any information about what a GeoSparkle has geometry association is. And then there's a whole bunch of stuff where we don't even have like the ontology to start to build this stuff around, and we're kind of just making things up for the sake of experimentation. So that's all to say, like, the work that we have to do isn't so much in schema or ontology design, but in modernizing and publishing the data models that we already have.
I see. Thank you.
Yeah, it was a great question. And that's, yeah. This little demo is pretty sweet. There's this science.ai had a little open source template for this JSON-LD. I have to call them out because I stole it from them totally unabashedly. It's a great little template to render the linked data value of the JSON-LD into the name, so you can actually kind of traverse all the pieces of the JSON-LD. It's pretty cool. All right, well, stay tuned for the outcome of the second ELFIE. Next month, I've got 2 talks that are potentials. One from some folks working on a project called scienceonschema.org. So Adam Shepard and Doug Fills, both ESIPers, have some really cool work that's pretty highly related to the technology stack and kind of the line of work that ELFIE and SELFIE are working on. So hopeful we can get that presented next month. There's a project out of Australia called the Location Index that's also playing in this realm of linked environmental data. And that kind of builds on one of the talks we had a couple months ago. So 1 or 2 of those, both of those are going to be coming in the next several months, and I'm hopeful to build a series of talks around this topic of kind of linked environmental features and samples and ELFIE, SELFIE. It's a ripe area to be worked on, as well as the OGC API stuff. So we talked about the upcoming sprint on OGC API coverages and analytics. There are a number of other sprints going on in that space. I look forward to some talks about that as well. So with that, thank you so much for coming along. Last call for questions. All right, this will be recorded. I'll throw it on YouTube and share a link. Thank you for coming along, and we'll be in touch.
Thank you, Dave.
Cool.
Thanks, Dave. Great talk. Bye.